Okay, are there any questions before we get started? Yes?
Last time you explained rings, groups and all that, right?
Right.
Why are they important?
Why are they important? Probably not very important. It's just good for you to know about it. Because sometimes you use group theory in solving electromagnetic problems, and sometimes you use ring theory in signal processing when you do fast Fourier transform, if you want to do algorithms or that kind of thing. Vectors are very important for us because you will learn that vectors can be generalized to other kinds of vectors.
No, but then from what you said, I got the idea that vector spaces have all the properties of groups, rings.
Not all of them, they don't share the same property. Okay. If you look at group theory, they have a certain definition of what a group means
You said
and what a ring means. Yes?
A group was closed under addition, right? Even vector space is closed under addition.
Yeah.
Addition of two vectors.
Yeah.
So, why do we bother about this lower levels?
Group refers to usually a set of objects that actually when you multiply two members of the object, the product remains within the group. You have this kind of property. Usually not addition, but usually it's kind of multiplication. And it's very important in studying symmetry of things. For instance, you can define rotation, 30-degree rotation, or maybe if you want to rotate certain things by 120 degrees, right? You define a rotation operator to be 120 degrees rotation. You take any members, any object rotated by 120 degrees, you form a new thing, and then you rotate by 120 degrees, you form a new thing, and then if you rotate by 120 degrees, it becomes an identity operator. So that kind of operations have the flavor of groups, rotations, translations, things that have something to do with symmetry. And there are many problems in physics that have symmetry, especially in crystal structures. So group theory becomes very important. So if you study electromagnetic theory, if you study photonic crystals, for instance, is an area in electromagnetics that has imported a lot of ideas from solid states, solid state physics and so on. And if you understand group theory, you can understand a lot of things to talk about in photonic crystals, for instance. So groups are not the same as vectors. Okay, vectors do not have these properties. Vectors are not closed under multiplications, for instance. Okay, vectors are generalization of Euclidean space. In Euclidean space, right? 1D, 2D, 3D space have vectors that we know from Euclid's day. Euclid, I look up the internet, he lives about maybe 300 BC, I don't know, maybe 200 BC. Long ago, right? And I think actually it's so easy to gather facts on the internet now. He lives around 300 BC. That was a long time ago. And then Confucius lived about 500 BC, and then Buddha lived around 500 BC. Lao Tzu lived around 500 BC, and Pythagoras lived around 500 BC. Okay, so all the people lived around that period. So Euclid lived around that period, and then, of course, from him we have what we call the Euclidean space. Euclidean space, and then you can define 1, 2, 3 vectors, and people go to n dimension, and we call the space Rn if you use real numbers. N-dimensional space, and then you call them those spaces Cn if you use complex numbers to form the vectors. Those are the Euclidean space. And then came Hilbert. David Hilbert, I also looked up the internet. He lived around 1862 to 1943. Okay, he started to generalize this kind of spaces to n-dimensional space and infinite dimensional space. And then you can have a function that also can be described as a vector. A function is a vector. So those are called the functional spaces. And then you can define inner product between vectors as what you did for Euclidean space. And then you can define angle between vectors. Okay, that's what Hilbert, I think Hilbert was mainly motivated by physics, and his infinite dimensional space were designed to solve many physics problems that came about during the period. And then you have another person by the name of Barnard. He is quite prominent also. Barnard, when did he live? He lived in a certain period. Okay, Barnard. He's from 1892 to 1945. Okay, he is about 30 years younger than Hilbert, as you can see. So he started to generalize what Hilbert did. And then he only talked about norm space and completeness of norm space and that kind of thing. Whereas Hilbert did vector spaces that are driven by physical motivation, but then he make it more general. And then, of course, later on, there's another person. If you're in electromagnetics, you often hear of him. Sobolev spaces. And he lived around 1908 to 1989. So he just passed away recently. Okay. So then you have another kind of norm space. And you talk about curve-conforming spaces, divergence-conforming spaces that you often hear about in electromagnetics. Those are Sobolev spaces. Okay. And who else came after that? I just learned that the method of moments actually came from Russia due to this Russian scientist. What is his name? Russian scientist. Actually, it's referenced in my book. I just forgot about him after 30 years. Okay, it's not due to Harrington. The method of moments came from this Russian guy by the name of Mikhail L. He lived from 1892 to 1942. So he overlapped with this fellow. So you can see that he lived during a period. And he was a Ukrainian, according to the internet. And he defended himself to be Ukrainian and refused to be a Russian. So he was sent to the concentration camp and he died in the concentration camp. Okay, that was a sad story about him. So let's look at infinite dimensional spaces for physical applications, which is usually called the Hilbert spaces. Okay, as you can see, you can generalize Euclidean spaces to infinite dimensional vectors. If these are infinite dimensional vectors, I can define inner product that I do for finite dimensional vectors in this manner very easily. Okay, this is a very straightforward concept. Except that when you generalize things to this manner, you have to worry about convergence. Not all vectors can be defined this way. When you sum over infinity, you have to talk about the convergence of these vectors. Okay. So then, if you think about this, then we can. This is an inner product that is actually used a lot in Euclidean spaces. I don't know if Euclid defined this kind of thing from 2,000 years ago, but inner product actually is quite common in geometry. You can define inner product between two functions. Okay, as the x. I think this is a review for many of you, especially if you're from physics. You have studied this kind of thing, but maybe people in engineering are not exposed to this kind of concepts as much. So this will be a revision for people from physics, but then repetition something quite new for somebody from engineering. Okay, so if you are to go to the computer and compute this, you will have to sum by using discretization. Maybe a kind of summations like this. If you were to compute this on a computer, you might do some summations by approximating this infinite integral, infinite dimensional integral that involve infinitely large number of numbers into a discrete sum. And if you look at this, oftentimes when we compute this in the computer, we will have to truncate this summation. Okay, so these are actually very similar in a sense in the practical world. We always have to approximate things, and then this inner product resembles the inner products that we have in Euclidean space. Okay, and then in mathematics, it's often a common practice to define inner product with a complex conjugation. It's often done with the complex conjugation. The good thing about complex conjugation is that you can define a length very easily. If these are complex vectors, these are complex vectors. Then if you define something with complex conjugation, then what you get is always a positive definite number. And if you have a convergence sum, this is always larger than or equal to 0. So you can use this to define the length of a vector, this kind of inner product. Whereas this kind of inner product, if this happens to be complex numbers, this need not be a real number if the two are equal, and then you cannot use this to define length. But this is important, in my opinion, in electromagnetics, this kind of inner product, because we also define something called a reaction. I usually call this the reaction inner product. And so like what we have in electromagnetics, we define inner product like this, where we don't put complex conjugations, and yet that inner product has a physical meaning. It's important, for instance, in defining reciprocity theorem. Okay, and this I usually call it energy in the product. Because essentially this is like the energy of the system. Okay, we take this magnitude square as energy of the system, and we have to make this distinction in electromagnetics. But if you read up quantum mechanics books, they invariably just use this kind of inner product. If you read up books in the math department, they invariably use only this kind of inner product. But we have to introduce two kinds of inner products because of this reciprocity theorem. Okay? So you can generalize this to complex conjugation of inner product. Okay, then that will be just that. Okay? And I explicitly put the complex conjugation here so as not to confuse these two definitions. In the math world, if you go to the math department, if you read their literature, okay, the inner product is invariably defined in this manner. Okay. If you read the physics literature, they use direct notation. Okay, instead of a comma, to put a bar there. And that inner product is invariably defined to be that. Okay? But I just feel that this inner product is not sufficient to describe electromagnetic theory. Because, as I said before, we have reactions that need to be defined properly. Okay? Are there any questions so far? So as you can see, a function can be thought of as a vector. A function is a vector. That's what Hilbert did. He studied this kind of infinite dimensional spaces created by functions. Those are called functional spaces and so on.
Both are the same, right?
What?
Both the definition of
Yeah, these are the same. This is math. This is physics. Okay, if you go to the physics department and study quantum mechanics, invariably they use this notation without fail. It's the same. I guess maybe this has descended from some great mathematician. This has descended from some great physicists. So this is direct notation. This is, I don't know what notation this is. Maybe this is Hilbert's notation. I don't know. But they would always use this kind of convention. Okay, let's see what we have then. Then, because of the fact that if you use this kind of inner product definition, then you can define what is called a norm. When you take inner product between two complex functions, if you use complex conjugation in the definition, then this always gives rise to a positive definite number. It's always larger than greater than 0, and a linear vector space with a norm defined, not necessarily this way, you can define all kinds of norms, like in Banach spaces and Sobolev spaces. For those who are familiar, norms are defined quite differently. This is just an example of a norm. The norm is some way of defining the length of a vector, and you can use this number to denote the length of the vector in the sense that if this vector is 0, this norm will be 0. If this vector is something non-zero, it will be a positive definite number. Okay? So those are called norm spaces, and of course you have other kinds of things, like you can use the distance between two vectors as being just the norm of their difference, as what you would do in the Euclidean space. Okay, this is called a metric. So, a linear vector space with inner product defined is usually called a Hilbert space. Okay, so these spaces can be infinite dimensional. So, and then of course you can have a norm space. And this is usually complete, okay? It needs something more than this, it can be complete, okay? With the inner product space defined, which is complete, okay? It's known as the Hilbert space. What is the concept of completeness? You can think of the concept of completeness as this, that if you are looking at real numbers, the rational numbers are closed. You multiply two rational numbers, you get a rational number. If you divide two rational numbers, you get a rational number. You add two of them, you get a rational number. But they are not complete. Because if you look at real line, on the real line, if you look at rational numbers, there will be holes between rational numbers. Those are called the irrational numbers, like pi is 3.1415965, 3962 or something. I don't remember what goes up to that, right? You can write an infinitely long decimal representation of that irrational number. So rational numbers together with irrational numbers forms the real line. Then the real line is complete. Okay, but those numbers, as I say, are called a field, and they are closed under addition, multiplication, and division. Okay, and you multiply two rational numbers, divide them, they always form a closed system, but they're not complete. But when we do computation in the real world, we always have to work with rational numbers. Right? We have to truncate a decimal place. That actually is a rational number. So in real-world application, we just work with rational numbers. But when something is incomplete, you can think of the system as having holes in the system that are not filled by your numbering system or your vectors. So when a Hilbert space is complete, it means that it has no holes. You can reach all possible kinds of vectors in that space, no more holes. Just like real numbers has no holes because it's filled by both rational and irrational numbers. Okay? This is the concept of completeness. But then, what is a Banach space? A Banach space is a complete norm space. As you can see, he came after Hilbert, so he studied what is called a complete norm space. The norm does not have to be defined like what we often do in physics, but the norm can be defined in many other ways. And as long as the space is complete, it's called a Banach space. I think there are some very obscure mathematical definition of Banach space, like for every convergence Cauchy sequence is a converging subsequence, and that proves completeness, and then there's Banach space. So lots of language, but you just have to think of it as a complete space, and then you have to learn what a Cauchy sequence is, and that kind of thing in defining completeness. Okay, then Sobolev space. Now, kind of different. Sobolev space, like when we have this kind of thing being defined, we always call this the energy of the system, and things defined in this way are also called the L2 space. L2 space are spaces of square integrable functions. Square integrable functions are very good in physics because they are related to energy. So all physical systems are square integrable. Okay, but Sobolev extend that to something more than that. It says that if a function is a member of the L2 space, if its derivative, maybe it's n derivative, first derivative, second derivative, n derivatives are all members of the L2 space. Okay, that forms a Sobolev space. So there is a kind of a smoothness constraint. Not all functions can be members of the Sobolev space. The functions has to be smooth enough so that if you take its nth derivative, this n can be a finite number, or maybe it can be a second derivative. Then that resultant function is still in L2 space. So the function has to be smooth enough. And this is very important for computation, because we often work with functions that are not smooth. And are they actually the good approximations of the real world? In the real world, everything is smooth, right? Electromagnetic field is smooth. Potentials are smooth. But when you do computation, you work with non-smooth functions. Okay, you have to worry about that. For instance, roughly you can see that electric field, magnetic field have to be members of some L2 space defined in higher dimension, because they are finite energy field. Okay. But then you can also see that curl of E is needed in Maxwell's equation. This produces magnetic field. So E plus curl of E has to be some member of the L2 space, has to have finite energy. Okay. So as curl of H has to be members of the L2 space. So we call that E and H are curl-conforming functions. Okay, and that actually is a way of defining the fact that they are members of Sobolev spaces. Okay, and then you have J. In electromagnetics, divergence of J must be equal to charge, right? So J plus J must be a member of the L2 space after you define that in higher dimensions. The divergence of J has also to be a member of the L2 space.
Why L2 space?
Charge has to be finite, right? We cannot work with infinite charge in this world. The charge that is produced physically has to be square integrable. So J has to have finite divergence. So this must be a member of the L2 space, and this kind of spaces are called divergence conforming. This is curve conforming. This is divergence conforming. Okay. Divergence conforming space. Yes.
So what about when we work with point source or light source or certain charge? Those things are not L2. They don't belong.
Charge. Even point sources.
Because the delta function is not square integrable. It's
right.
integrable.
Delta function is not square integrable. You're correct about that. Delta function is not square integrable, but you can also think of that. The delta function is a fictitious source. It's actually idealization of some real world source. Real world sources are always smooth. Okay, there's no true point charge in the real world. Okay, so if you work with computation, if you work with real world sources, they're always square integrable. They always have finite energy. So the currents, the fields and the curve conforming the sources have to be divergence conform. They have to be member of the sublab space. Are there any questions so far? Yes.
What if E is result on the interface of two different materials? It is still in the L2 now.
Right. If E is at the interfaces of two
Different materials.
media, its curl is still finite. You can prove that quite easily, right? Curl of E is I omega mu H. Okay? There's no singularity on the right hand side. Even if you have inhomogeneity, curl of E is finite. It has to be finite, and hence it should be square integrable. Okay, it should be square integrable. I think that's the case. Curl of E, curl of H, curl of H. I guess if you put current sheets there, you will make this non-curve conforming, but for all real world current sources, this has to be curve conforming. Okay, you can put fictitious current that are current sheets there that are not square integrable, and yet you can make this non-curve conforming. But for any smooth region of the space, they have to be curve conforming. Okay, except for interfaces where you put in the current sheets, which can be thought of as artificial, and then you drive the curl of H to be non-curve conforming at the interface. And you will have a jump discontinuity. Okay. This is a good point because in real world things are smooth, but in an idealized world we put in non-smooth sources and so on. Okay. So let's talk about. So we can generalize vectors from Euclidean spaces to infinite dimensional spaces to include functional spaces. And functional spaces are infinite dimensional, and those spaces are usually called Hilbert spaces. So let's talk about linear operators that we often use so often in electromagnetics. Like Green's function, 0 to a g x x prime, f of x prime. The x prime is equal to hx. This is an integral equation, okay? And you can always get integral equations in electromagnetics quite easily. For instance, if I were to ask you to solve for the capacitance of a sphere, an object that is very odd in shape, this object has infinite conductivity, and then it's charged through a certain potential V. Okay, a by adding charges to this object. As we know from our physical understanding, all these charges will repel themselves and they will be pushed to the surface of the object. So there will be some surface charge distribution on this object. Okay? And then we all know about Green's functions. Green's functions are solutions to this equation. Okay, that's Green's function. We actually have solved this solution. It's equal to 1 over 4 pi r minus r prime. Because we have solved the dynamic case. In the dynamic case, it was this. You did this for part of your take-home exam. So for static case is equal to that. Okay. Then, if you were to solve Poisson's equation says that the potential is due to the charge of the system. Let's assume that everything is in vacuum, so this is the Poisson's equation, I believe. Then the potential, by the principle of linear superposition, is just equal to the solutions to the point source problem convolving with the distributed charges that we have over here. So the equation then is equal to this one, a convolutional integral of 1 over r minus r prime rho of r prime over the volume of the charges, right? The volume of the charges. This is what the potential would be produced in the case of the thing. And then if this is a surface charge problem, we need only to integrate over the surface area of the thing. And then this is my surface charge problem. Okay, this is potential. And this is for R anywhere. For R anywhere. And I can form an integral equation very easily. So this is a rudiment of an integral equation. I say that phi of R must be equal to V for R belonging to the surface area. Let's call this surface area S. Okay. This must be the boundary condition for that electrostatic problem. And then if that is the case, then you form an integral equation right away saying that V must be equal to 1 over 4 pi epsilon the S prime. Then we call this the S prime. S prime means integrating over the prime variable rho S R prime over R minus R prime S. And then this has to be imposed for R belonging to S. So this is the rudiment of an integral equation. Okay, so V is known. This is unknown. You have to figure out how to solve this integral equation in order to find the unknowns of the problem. And once you have done that, if you know the charge, then you can go back to this equation and find the potential. This is a very simple electrostatic problem. You can do similar things for electrodynamics. But what I was trying to get to is that operator equations come about in electromagnetics all the time. Equations of this kind. This is in 3 dimensions, and I just write a very simple one for 1 dimension. You can also solve this kind of problems for 1 dimension. You will have this kind of operator equation. You can think of this operator equation if you were to approximate it with the discrete summations. If you approximate this integration with discrete summations using quadrature rules, all of you know how to do quadratures, right? I presume that you know how to do numerical quadratures. So this actually is very similar to something like this. Fj is equal to hi. Very similar. So this actually is very similar to a matrix equation. The matrix G dot with the vector F is equal to the vector H. So operator equations are, in a sense, very similar to matrix equations. And then I guess I can erase this now, since I have derived the integral equation for you. And this is just one kind of operator equation, integral equation. Another kind of operator equations are what you encounter in physics all the time, and electromagnetics all the time too, is that if you have an equation of this sort, x might be between A and B, for instance. This is a ordinary differential equation. Usually this equation is quite easy to solve if k is a constant. But when k is not a constant, it's quite difficult to solve. There's no closed form. So you have to resort to numerical methods in solving this equation. And we can think of this equation as just an operator G operating on F is equal to H. You can also think of this as an operator D, which is actually a differential operator operating on a vector F, okay, is equal to a vector H. You can think of these functions as vectors. Okay, so are there any questions so far? Anything that you are not familiar with or like to ask more questions? So this is called a differential operator. This is called a integral operator. The difference between an integral operator and a differential operator is that integral operators involve points that are related by Green's functions, such as this one. Okay, so every point is related to every other point.